The purpose of this experiment is to design a spectrometer whose parts can be printed by a 3D printer and can be used by a smartphone. In this experiment, we used an iPhone 7. The spectrometer would then be used to take spectra of incandescent light bulbs, which will be compared to the intensity spectrum produced by a blackbody of a similar temperature. A spectrometer is an instrument that uses a diffraction grating or prism to split emitted light into a spectrum of wavelengths. Here we can see a spectrum of the visible wavelengths taken in this experiment of a Mercury fluorescent light bulb. The fluorescent light bulb is not a blackbody or a graybody, so we notice that it looks as though there are dark lines in the spectrum. This is where no light is emitted from the material. A blackbody, on the other hand, like the spectrum of the incandescent light bulb, should have a continuous spectrum with no black lines and a growing intensity until the maximum wavelength. A blackbody is a body that reflects no light from its surface, thereby perfectly absorbs all incoming light. Thus, the only light emitted by blackbodies is due to thermal radiation. The sun is an example of a blackbody. Although it does not perfectly reflect all light from its surface, the amount of light reflected is small enough that it can be treated like an idealized blackbody. Incandescent light bulbs also mimic blackbodies, returning very little light in comparison to what they emit due to thermal radiation. However, because they are not close to an idealized blackbody, they are called greybodies. The two concepts important to blackbodies are Planck's equation, which will give an intensity at a particular wavelength for an object of a given temperature T, and Wien's displacement law, which is derived from Planck's equation and shows that for a blackbody of a given temperature, the maximum wavelength can be calculated. For this experiment, we used incandescent light bulbs of 40 and 60 watts, which had corresponding temperatures of 2500 Kelvin and 2700 Kelvin. Our spectrometer is printed into 4 parts, then superglued together into one piece. The phone case keeps the actual spectrometer snugly attached and flush to the iPhone camera. The diffraction grating was glued to the attaching piece and then to the slanted end of the tube. This was then attached to the phone case so that light would be directed into the diffraction grating at a 45-degree angle to produce a spectrum of visible light. The aperture is attached to the other end of the tube to limit the amount of incoming light and help in dealing with saturation. In order to limit oversaturation, our images were taken in a windowless room with no other ambient light beyond the light bulbs. A standard 120-volt lamp was used to power the light bulbs. We took images of 3 spectra, the 60-watt and 40-watt incandescent light bulbs to test, and a fluorescent mercury bulb for calibration. Here are the 3 spectra we decided to use for our data. We took multiple pictures, and these were the best representations of the spectra with the most reduced saturation. There is still some inevitable interference that is accounted for in our results. Our calibration was done with Spectral Workbench, an online resource that calibrates spectrometer results using known spectrums. To use the site, you upload pictures of the spectrums, and it analyzes and graphs red, green, blue, and overall intensities. We used a fluorescent light bulb with Mercury to calibrate our spectrometer by uploading our Mercury spectrum and manually aligning it with the known Mercury wavelengths using the site's calibration tool. The wavelength spectrum found through this method can then be applied to other spectrums so that they are calibrated to the appropriate wavelengths. Initially, we expected to analyze the data with Spectral Workbench, but it became apparent that the graphs created there wouldn't suit our needs. Instead, we read the images into a Python code and graphed their intensities versus the wavelengths to see if we fit the desired shape. Our graphs, shown above in blue, did not fit the blackbody curves like we wanted, which are shown in red and green beside them, but this was also something we expected, due to the errors encountered throughout the experiment. As a result, our experiment was inconclusive. While we did get working spectrums from our 3D printed spectrometer like we intended, Our data did not provide an appropriate demonstration of the blackbody effect. This was due mostly to three causes. Light interference in the spectra was an issue, as it resulted in oversaturation and ambient light in the images. While our environment removed all light except that coming from the light bulb, light reflecting off the walls and from the light bulb itself interfered with our data. Also, because the light bulbs are not perfect blackbodies and are instead graybodies, there was some light that reflected back from the light bulb from itself. There are also the limits of the spectrometer. While 3D printing a spectrometer is convenient, our iPhone cameras lack the appropriate technology to read infrared light waves, which is a significant portion of the light bulb spectra. In addition, the spectrometer provides many technical issues. In order to fix these issues, I would recommend that in future experiments, a more controlled environment is used that reflects less ambient light. A better spectrometer is also recommended. If 3D printed, the spectrometer should have a higher resolution and a design that fits together better when assembled, so that less ambient light gets inside the spectrometer and a clearer spectrum can be taken. More accurate analyzing methods should be used to better match each spectrum with its according range of wavelengths and produce more precise data.